Weather, one of the most astonishing forces on Earth, capable of both devastating power and spectacular beauty. Wherever you live on the planet, weather shapes your world. Yet for most of us, how it works is a mystery. To really understand weather, you have to get inside it. So I'm going to strip weather back to basics.
All in the name of science.
Uncovering its secrets in a series of brave, ambitious, and sometimes just plain unlikely experiments.
Well, it certainly feels like a dust storm from here.
To show you weather like you've never seen it before. All weather, no matter how rare or how unusual, can be broken down into three simple ingredients: wind, water, and temperature. With just those three things, you can create pretty much any weather you want. But the most important of the three is temperature. In this program, I'll discover how without it, we wouldn't have any weather at all.
Oh, yeah. Oh, that's a lot of dust now.
How a dust storm in Africa can make rain right here. And how heat can produce snow as hard as concrete. Almost all our planet's heat is provided by the sun. And we tend to think of the sun as the source of all our best weather. But if you're looking to unlock the secrets of the weather, the heat coming from up there is not as important as when it's coming from down there, from the ground. I know it sounds unlikely, but it's all to do with the fact that the sun heats the earth unevenly. Sand gets hotter than water. Tarmac gets hotter than sand. Concrete gets hotter than grass. And these differences produce pockets of warm rising air called thermals, which drive winds and create clouds. But how can you see that effect for yourself? Well, with a quarry, 5 vehicles worth of kit, and 2 specially built metal tables. These tables are going to be our hot ground. Because they're dark in color, they should soak up lots of heat from the hot sun. And to make sure they get hot enough, we're going to give the sun a little help. With 14 gas canisters, all connected up to 18 high-power burners. We reckon with these we can get our table up to 200 degrees C, maybe even higher. And I'm hoping that's enough to show you what hot land does to our weather. To be perfectly clear, my ambition here is not to actually make weather with this. I'm not hoping for a little square cloud overhead. The theory is right, it's just the scale is a bit small. What I will be doing is creating that rising column of air, that thermal, which is part of the weather, and it is something I will be able to show you once I've got it established. So let's do just that. Turn on the gas, fire up the burners, and get those metal tables as hot as we feasibly can. enabling me to fly some paper helicopters. Yeah, I know, but bear with me.
Hello.
There is method in this.
Can I have my box of... Thank you. Right. Going up.
Time for my high-tech thermal indicators. Now, normally, a paper helicopter would just spin slowly to the floor. But it doesn't. It hovers.
Fly! Oh, there you go, there you go, there you go.
You can see how we've created a thermal down there, and the helicopters that catch it are flying in that column of rising air. The updraft is enough to hold the helicopters in place, just as they do naturally with clouds, raindrops, and hailstones.
Oh, yeah.
But as the heat coming off the metal table increases, the helicopters begin to climb, until they're disappearing out of sight, which is how it should be. A real thermal can reach 1,500 meters, and they have an important role to play in our weather. We've all seen how puddles dry up on a hot day, but where does that water go? Well, those thermals take it up into the air until it gets high enough and cold enough that it condenses back into drops and forms a cloud. But there's another result of this uneven heating of the Earth. It produces deserts. And deserts play a very important role in what happens next to those clouds. It's hard to imagine, I know, but right now I am surrounded by desert. And not just any desert either, probably the most famous desert of them all, the Sahara. Because Saharan sand regularly makes it all the way to the UK, where it leaves a fine, dusty layer on cars, benches, windows, pretty much everything, in fact. Which is more than a little surprising, because it comes all the way from Africa, more than 2,000 miles away. So how on earth did it get here? Well, first you need a particularly sun-parched part of the planet. And then you need a dust storm. Dust storms are the way nature gets dust off the ground and into the air. A big one can easily be a mile high and 100 miles wide. A vast, moving wall of dirt. But even the big ones only travel between 25 and 50 miles before they die out. So how does the dust end up 2,000 miles away on the bonnet of a car in Bristol? Well, believe it or not, it bounces there. Let me try and show you what's going on. Imagine this tennis ball were a grain of sand. Drop it from waist height and it bounces up about 2 feet. Now imagine this ping pong ball were a smaller particle of dust. Drop it from the same height and it bounces up about the same distance. But if I drop them both together, watch what happens then. Yeah, the ping pong ball flies off. What's happening actually is the ping pong ball is smaller and lighter. All the kinetic energy, the bounce in this ball has been transferred into it and away it goes. Obviously, real dust comes in many more than just 2 different sizes, which is why this is maybe a better analogy. 4 different sizes of ball this time, stacked loosely on this plastic spike in the centre. Obviously, real dust doesn't have a plastic spike connecting it, but your alternative is you watch for 10 hours whilst I try and drop all 4 in a line. Let's see what happens this time. It's gone. The small ball is, I mean, it's just, I'd show you again, but I'll have to wait for it to re-enter the atmosphere, I think. Seriously, it's gone. So that's the principle. But can actual dust really do the same thing? Even with the power of a huge dust storm behind it? To find out, I'm going to the source of most of the world's dust. Not the Sahara, but South Australia, where Dr. Craig Strong has offered to help me start a dust storm of my own. What are you actually looking for?
Well, I'm looking, Richard, for the landscape that's going to produce dust. And I think this stony plain is probably really good because you can see these rocks. They're acting as a trap for dust. So I think if we dig down, we'll find that there's plenty of dust. It's just that means it hasn't blown away yet because of the rocks are locking all that dust in.
So when I see an area of rocks like this out here, I assume all the dust has gone. You think it's trapped underneath?
Absolutely. So if we have a look down here, Richard, once we get under there, it's just dust gold. You know, look at this.
It's incredibly fine.
And see that just blown away. So there's lots and lots of fine material. This is exactly what we want. That's what dust storms are really made of.
The problem here is that the dust is trapped under these stones. That's why you know it's here, but it is trapped.
Absolutely.
How do we get it out?
The rocks are doing the job of protecting the soil, so I reckon we probably should pick up the rocks and move them out of the way. That's the first step.
Churn it up a bit.
Turn it up a bit, that's right.
That's easy. I can do that for you. I'm going to take its head. Well, I say me, but actually I mean this chap, Trevor, who just happens to have the very tool for pushing aside all those stones. It's not long before he's cleared an oblong area the size of a couple of football pitches. And it has an immediate effect. Look at that, dust devil. That's amazing. Probably those swirling winds come through here all the time, but because we've taken the stones away and uncovered the dust for it to be picked up, we can suddenly see them. It's beautiful. But it's not what we're looking for. We want to make something just that little bit bigger. One dust storm coming right up. Right, where do you want it? Here, I would say. This'll do nicely. Doing this in what is effectively the home of half of the world's dust. Hope I don't trigger an international incident. You get up tomorrow and your sideboard's covered in dust, because I started this. That's a lot of dust. I don't know who that bloke is. Just a helpful local decided to lend a hand. That's good of him. Our blokes live round here, happy to come out, all in the name of science. Yeah! Now we're talking. This is a dust storm. Oh, that's a lot of dust now. And it seems to be working. In amongst all the cars and chaos, the dust is starting to bounce. Individual grains are colliding against each other, just like the rubber balls did. And notice that they're not just bouncing in the direction of the wind, they're being propelled upwards. Well, there it is. We've got the dust bouncing just like it does in a real dust storm. But in a real dust storm, it bounces much higher than the storm itself. Can we do that here today? There is only one way to find out. Craig has brought in another dust expert to help, Professor Nigel Tapper, who specialises in measuring airborne dust. With his assistance, we should be able to see just how high we can get our dust to bounce.
Okay, beautiful.
Nigel, to be honest, it looks like this is something you're about to fire at your balloon. What is it?
We've got a pump arrangement here that pumps at about 2.5 litres per minute through this cyclone sampler that we can put underneath the balloon to sample dust at various levels. That was a fly.
Yeah, they're quite tasty.
And, yeah, they're
good.
beautiful.
They're not bad. They're not
They're
bad.
particularly tasty here at
Bit
Malura.
dry.
Yeah.
So tie it onto the balloon string then.
Yep. I just got to run it through here. This is the tricky bit because you've got to remember which way to roll it.
Oh yeah.
There
I'll
we
do
go.
this one. I'll do
and
this
we do it on the bottom too.
Watch this go well.
Yeah,
Hold
you-
on.
you
It's
do
that.
that.
I've got it. No, watch. It's that way.
Ah, perfect.
You
did it
see?
well. You've done that before.
Well, no. Why would I have done this before? Ever.
Okay. Winching up.
We're winching, not whinging. That's a pom joke.
Yeah, I know.
Yeah, all right. I just chucked it in. Nigel plans to put 3 dust samplers under the balloon. One at 3 metres, which was about the height of the cloud we created with the cars. One at 8 metres, more than double that height. And one at 20 metres, because, well, that's how much string we've got. That extra vane at the top is carrying a miniature camera, so we can keep a close eye on what's going on. And to make sure we're doing our very best impression of a real dust storm, we've wheeled in a couple of enormous fans to supply some extra wind. So my job now is to try and keep the balloon, which is suspended from the winch over there through this hook, at the right height and in the best place to catch the most dust kicked up by our dust storm. And one important thing to bear in mind, this all seems very big. I mean, it's a very big balloon, we're using big tools to make the dust, but we're imitating the weather. This whole experiment, in fact, is tiny, but the principles are just the same. And hopefully the fine particles will end up on top. Or me, if this balloon goes much higher. I did point out to them I'm the smallest bloke here. Why I've got this job, I don't know. We'll be all right. Right, we're ready. So the vehicle is churning the surface. The fans do the job of the wind. Maybe I should have put my goggles on. That would have been better. Well, it certainly feels like a dust storm from here. So now I just need to keep the balloon in the densest part of it.
I'm going to go over here a little bit.
Basically, if I can't see or breathe, then I'm probably in the right spot.
The different pumps at different levels are sampling the air and the dust carried by it at different heights. There's no way could these fans actually blow the dust directly onto 10 or 12 meters, but they do inject the energy into the system. It's an exchange kinetically, the particles bouncing off one another, hopefully ending up at the top.
But there's only one way to know for sure. Check what's in those pumps. Luckily, Nigel has a makeshift laboratory right on site.
It'll be really interesting to crack these open and see what we've got. We've got to be a little bit clean here.
What are you trying to say?
All right, now we've got the insults out of the way, time to see what we collected in the lowest pump. And if it's not dust, we've got a problem. Because that was slap bang in the middle of our homemade dust storm.
Okay, beautiful.
Oh, there it is.
We were only sampling for a short time, and there's a lot of it, as you can see.
So let's move up a level
Okay.
to 8 meters up into our homemade dust storm and see what
That's right. So let's have a look at the filter paper. Turn it over. Whoops, we've got a slide. There was
there
a
it is.
little bit of smudging.
Yeah.
So we've actually got a bit of fine material at 8 meters.
So now at 20 meters,
At 20 meters,
which was well out of the actual
Absolutely.
cloud of dust. If there is any here, this is the finer particles that have managed to bounce themselves up well beyond the top of our plume of dust.
come on. Turn it up the right way. There we go. Well, look,
There is smudging on it.
there is a smudge, so we did get a bit of material up there.
Definitely some there.
So I think we can count that as a success. We've got dust at least 5 times higher than our cloud.
So we must bear in mind, I mean, this experiment, though to us it was quite big, it's actually tiny. In terms of the weather, it was minute. So this upper level, for us 20 meters, that was outside of our plume of dust.
yeah.
If that were scaled up to be weather, to be a dust storm, that could be thousands of feet high.
If we were looking at a real dust storm, and they could get up to 3,000 meters, it's an amazing process.
A large dust storm can move 15 million tons of sand in a single go. Many are so big that they can be seen from space. And when that dust has bounced high enough, it gets caught in global wind patterns, which move it around the planet. Once in the clouds, dust plays a crucial role in our weather. Because dust is central to the story of rain. Water vapor needs something to stick to if it's going to turn into raindrops. And dust is perfect. So down the dust comes, carried by the water drops. Out of the sky and onto your car. So without the sun beating down, creating deserts and dust, you might not get rain. Kind of ironic, isn't it? But there is one rare type of rain that doesn't need dust. What it does need is cold.
It's a weather phenomenon unlike any other. One that can take any of these objects and trap them like flies in amber, encasing them in a hard, plastic-looking shell.
It's called freezing rain. And as its name suggests, it's completely dependent on temperature. But it's not just the weather that needs to be below freezing. the rainwater does.
And I'm going to try and recreate it for you, right here, right now. Actually, I'm probably in the best possible place to do that, Montreal, Quebec, Canada, because it happens more here than just about anywhere else in the world. Right. Oh yeah, that's perfect. Really very cold, which is what I want. The air temperature here right now is about -10 degrees C, but as long as it's somewhere near freezing, the air temperature doesn't matter. It's the temperature of these objects.
I need them to be really cold, and they definitely are.
So, I've got water that's below freezing, but it's still in liquid form, and I've got a hose. Let's see what happens when super cold water hits super cold objects. It's not complicated. I've begun.
Well, it might not be complicated, but it is effective. The moment the spray hits the hydrant, it turns instantly to ice. Fully formed blobs of ice that appear right in front of your eyes. Instead of dripping into icicles, it solidifies immediately. So, how does it work? We've already seen how raindrops need an impurity like dust to form. But freezing rain is formed when a snowflake falls through a freak layer of warm air on its way down. Now it's rain, but rain without any dust inside it. The temperature of the drop can go below freezing without turning to ice, until it touches something cold. To try and recreate that, I'm spraying distilled water.
Starting. This I feel is good, but it's going to take a while. I could be patient and wait, or just tweak my approach a bit. Bigger, which is better.
The water in the truck has been outside for days, so normally it would be frozen too. But fire trucks in Canada have a constantly revolving drum inside them that keeps the water moving, a bit like a giant slushy drink dispenser.
This is strangely addictive. I mean, I've done a little bit there, and now I just want to do everything, more. Let's have a go at this.
Certainly, it gets the job done quick. So, let's see what we've got.
Look at that. Completely encased in crystal clear ice, and that's exactly what I want.
It's the clarity of the ice that makes freezing rain so unusual. That and the fact that it completely surrounds any object it touches. It's not just icy where the objects face the hose. It's icy everywhere, in a perfect, even coating, leaving the objects rigid but unharmed. Ish.
There's going to be shouting about that.
Luckily, freezing rain is fairly rare, but it does hold the secret of how we get frost. Just like our fire hydrant and phone box, these leaves have cooled below freezing. The difference is, frost grows without falling as a liquid first. The ice crystals just magically appear, literally out of thin air. But when ice crystals grow in the air instead, then something even more magical happens. They become snow.
All snowflakes start off as an ice crystal, a six-sided shape, a bit like this.
But then temperature begins to play its part.
Just a little extra moisture in the air and arms start to form at the corners. A degree rise in temperature and a plate forms on one of those arms.
A 2-degree drop and tiny needles form around them. Each of these minute changes stamp their identity onto the ice. And they are so subtle that scientists aren't sure exactly why it happens.
What they do know is you end up with something like this.
A snowflake, water in its most beautiful and complicated form.
Except I made this one. It's all my own work. Nothing at all to do with professional snow artist Simon Kemp over there, who's just out for a picnic. Well, I did the fiddly bits. I did that bit. That's mine. All my own work. The really cool thing about all of this is that every one of these shapes is different. I know it's a bit of a cliche, no two snowflakes are the same, but they're not. I guess because of this, well, infinite number of variations in temperature and humidity, every snowflake really is unique. Not just in a handful of snow or in all the snow in this giant snowflake, but all the snow that's ever fallen in the world or ever will fall.
That's because the conditions that create each snowflake are so unique that an individual shape can never be repeated. But what's really amazing is that a snowflake never stops changing. Even after it's landed, temperature continues to transform it in the most surprising ways. I'm interested to see exactly how.
So I thought I'd kill two birds with one stone. Provide a civic service for the good people of Davos by clearing this car park. Sorry. And conduct a little experiment. But it's more of an illustration, really. Yeah, we're ploughing.
First off, I need to compress the snow as hard as I can.
Manly work taking place. One last load. Right, I'm going to give it a real press this time. Come on. Yeah. I think that's about as solid as I can get that. Inevitably, the hardness of snow is something scientists have considered, and they've developed a scale associated with it. 5 stages, and it goes like this. Can you push a fist into it? No. Next down, 4 fingers. This isn't as rough and ready as it sounds, actually. The fist equates to 10 grams per square centimetre of pressure. After the 4 fingers, it's a single finger. That's 100 grams per square centimetre. No. If all of that fails, they move on. Get serious. A pen. Yeah, so it would end there, but if that doesn't work, the next scale is a knife. I haven't got a knife. I have, actually, just for the purposes of this. Yeah, I know. And then they see if the knife goes in and, oh look, it does.
haven't actually done that just because I happen to have a sword in my snowplow truck. There is a reason. This is all about the changing nature of snow, the fact that it never seems to stop altering. I've made it into this big mound and made it as firm as I can, but it's not finished there. Unless there's a sudden heat wave, by tomorrow morning, another significant change will have happened, and I may have set the locals an interesting and unexpected challenge with my sword in the snow. Mustn't forget my pen.
Overnight, the snowflakes undergo a remarkable change. All the arms and branches broke off as my snowplow crushed them up next to each other. And now they begin to fuse together in a process scientists call sintering, joining on to each other and the blade of the sword in one rigid structure. This isn't freezing. In fact, the whole process works better when conditions are slightly warmer. It's restructuring. The next morning, we hid our cameras in a nearby shed thing and waited for the first curious locals to come past. The sword is fixed as if it's set in concrete. This isn't ice, remember. It's still snow. Snow that never stops changing. All because of temperature. When we think of temperature, we tend to think of sunshine, or lack of it. But in fact, the biggest influence that temperature has on weather is controlling the water vapor in our air, evaporating it from the ground and the oceans, freezing it into frost and snow, or condensing it into fog. I've come to one of the most predictably foggy places on the planet. The Appalachian Mountains, near Blacksburg, Virginia. Almost every morning, fog rolls up the Bluestone River and floods the valley.
This must be one of the off days. Which is why it's just as well I'm on this particular road, because here they can make their own fog at the flick of a switch.
This is the Virginia Smart Road, a 2-mile highway designed to test vehicle and traffic systems in different sorts of weather. However, we're going to use it to take a short diversion and answer a question I've often wondered about. If fog is made of water, then why isn't it clear? Why is fog white?
Do you know, I never noticed how loud fog is. It's loud, isn't it? Oh. London in Victorian time must have been deafening.
Luckily, we're not planning on doing anything with sound. We're doing it with light. Light is made up of lots of different wavelengths, each a different colour. And we see those colours when objects absorb one wavelength and reflect another. The light from this laser is scattering off the tiny particles of fog, making each one visible. But we are only projecting one colour here, green, and they're reflecting it. The air around them hasn't reflected any wavelengths, so it looks black. project red and the droplets change colour. Same thing with violet. In fact, they reflect every colour. Add all the different ones together and they become white. Fog is just a cloud that's in contact with the ground. So the reason fog looks white is the same reason clouds look white. Because they're scattering every colour of light.
Now, you might be thinking, hold on, clouds aren't always white, sometimes they're black. Well, yes, sometimes they appear to be black, but that's mainly an optical illusion. It's your brain exaggerating any differences there are to give you what it thinks is a more useful picture. And I can demonstrate. I've cut 2 holes in this piece of cardboard, and if I put one hole over a white bit of cloud and one over what looks like a black bit, in fact, there's barely any difference. And what tiny difference there is caused by those minute water droplets fusing together to form raindrops.
The bigger drops of water make the cloud more dense, which makes it harder for sunlight to pass through. So we see dark patches that our brain exaggerates. But sometimes there's no doubt that a cloud is black. The sort of brooding storm cloud that serves as warning for one final type of weather. The type that no show on weather should be without. And it's a fitting conclusion, because it requires all 3 of the key ingredients that we've looked at in this series. Temperature, water, and wind in equal measure. When heat makes the ground intensely warm and the air is heavy with water vapour and strong winds mould the clouds, you create a lightning storm. This is one of the planet's most lightning-prone regions, Florida, USA.
For most of us, the most dramatic weather we're likely to encounter is thunder and lightning. We've all heard thunder and seen lightning. But here's the interesting thing. It is actually possible to do the exact opposite, to see thunder and hear lightning.
And I'm going to show you one way to hear lightning right now, without even leaving my car.
Right, first of all, turn the radio on. Right. Then tune it to the AM frequency, because this works best on that.
And then look for a point where you haven't got a radio station. Yeah, it's tricky. There's a lot of radio stations in the States, but here we go. There. Right, between radio stations, what we've got, well, is static. Not surprisingly, I know, but some of that static is quite important to us. Listen for those quite distinct pops. Those are lightning strikes that might be happening some distance away, but the huge electrical discharge is interfering with the radio signal. So we're listening to lightning happen. And this system is so reliable that storm chasers actually use it to track down storms. The louder the pops are, the nearer the storm is.
Let me just prove to you that this is electricity making this happen.
Never could do this. the static electricity I've built up on the balloon affects the radio too.
See? Static. It is interesting, but no matter how effective or sometimes useful that method is, it isn't the real and actual sound of lightning. To get closer to hearing that, I need to set something up.
Because static isn't the true sound of lightning, just as it isn't the real noise of a balloon. This is a very low frequency detector, and it can pick up lightning strikes from thousands of miles away. Too far away for any static to be an issue. As the planet has more than 100 lightning strikes a second, I should have a fairly good chance of hearing a few between here and the other side of the globe. What you're listening for particularly is whistles. And that is the actual sound of a lightning bolt somewhere on the planet. But if this is the real sound of lightning, then what is thunder?
I've got another balloon here. Don't ask me why. Just have. Now, what happens next is no big surprise. There's a big bang. But what is surprising is where the noise comes from, because it's not the material of the balloon. If I stretch the rubber like so and pop it again, there's no noise. The noise is coming from the air.
As the balloon bursts, the air inside it explodes out, and that is a clue to how thunder works. But to find out more, I'll have to visit one of the few places in the world capable of creating full-blown thunder. They do it by firing 200,000 amps of electrical current down this narrow copper wire. Exactly the same amount as in real lightning.
So this is it. This is where it's all controlled.
Yep. So you'll need a pair of these,
Will I?
which is going to be quite loud.
Is it?
Because you're going to be producing thunder.
Okay.
And
Right.
also, don't look directly at the arc because it's very bright.
Right, so I've come quite a long way to see something that I can't look at or listen to.
Pretty much.
Good, okay, brilliant.
Well, I suppose it is quite a lot of electricity we're playing with here.
If your kettle goes off, he's nicked your electricity to put in their capacitors. Okay, these on?
Yep.
Go. Have we started?
Yeah.
Right.
So now we can see the voltage on the capacitors.
Oh, yeah. So essentially this is going to build up a colossal charge and then discharge it.
Yep.
Dan,
Yep.
I can hear what you're saying.
Oh, yeah. Also, when the shot goes through, you might want to put your hands over the defenders as well because it is quite
Shall I
loud.
just cower under the table?
Oh,
I
you
mean,
could
I
go
don't
on
mind.
the table, yeah.
Right, it's 25.
Yep, we're nearly there. Okay, so we're ready, so we can fire.
But I can't look.
Yeah, we can't
Or
look.
listen. I imagine. Oh! That, in fact, was quite staggeringly loud.
Yep.
I mean, really amazingly loud.
Yep.
So, was that thunder, or was it just sort of the discharge of the electricity leaving and arriving?
No, that was thunder.
But it didn't sound anything like thunder. It was just like that.
Yeah, and that's because the lightning arc is only 20 centimetres long here. In reality, you've got a kilometre of an arc that's all producing sound on every little bit, and it all arrives at you standing a couple of kilometres away at different times.
Because a bolt of lightning is around a kilometre long, some of it is further away from us than other bits. So parts of the sound get to us quicker, meaning that what we hear is multiple rumbles of that short, sharp bang. But it still doesn't tell us what thunder actually is. Luckily, Dan has a way to show us, using slow motion cameras and a line of lit candles.
It's the director's birthday. We've got another 56 candles to go. We're getting there.
Once again, we return to the control room. The candles are all blown out. And if you watch carefully, you can see that they're blown out one by one. So what is going on? Well, of course, it's all to do with temperature.
A typical bolt of lightning is somewhere between 2 and 5 centimetres wide, so something close to that. These, by the way, are not for style reasons, they're for protection, because effectively I'm taking a shaft of sunlight as wide as this screen and focusing it down to something roughly the size of a bolt of lightning. It is hot, but it's nothing compared with lightning. A typical bolt will reach 20,000 degrees Celsius. That's well over 3 times the temperature of the surface of the sun itself. Thankfully, it only lasts for about 1/10,000th of a second, but that's still enough for something quite amazing to happen.
Because lightning is so ferociously hot, it explodes the air around it, causing it to rush outwards, like the air in my balloon. What we see with the candles is that air moving away from the lightning bolt in a shockwave. But just how powerful is this wave? Time for another experiment. Can thunder break these glass light bulbs?
Well, I agree light bulbs are delicate, but are they delicate enough to be affected?
We think so. We certainly think that the inner ring of light bulbs will go. I'm not quite so sure about the outer ring. One way to find out.
Zap!
Yes.
They've been destroyed by the sheer force of the hot air exploding outwards. Well, except that tough one at the back. It hardly flinched. But still, pretty impressive.
I really want to see this one because I still can't believe it was strong enough.
Okay, let's have a look.
And that's a heck of a wave.
Notice, it's not the lightning destroying the light bulbs. The arc never even touches them. It's the shockwave after the flash that does the damage. Notice also that the sound of thunder happens even later, after the flash, and after the bulbs have exploded.
And that is a lot of power, isn't it? A lot of energy.
Yeah, and that's just from the thunder. Like, the arc hasn't attached to the light bulb, so that's just the shockwave that's broken the light bulbs.
Which tells us how strong that shockwave can be.
But I want to see more.
What we've been looking at, impressive though it is the effect of thunder. I want to look at the thunder itself.
With very specialized cameras, we can actually attempt to capture that shockwave on screen. Not the effects, but the actual shockwave itself.
That's fantastic. That's absolutely brilliant.
That is the air exploding away from the hot lightning bolt. at over 700 miles an hour.
I think we can count that one a definite success.
So there you have it. You can hear lightning. And you can see thunder. All because of the incredible temperature it gets to. We've seen how temperature drives weather. How heat gets water into the air. And cold turns it into clouds. How warmth creates winds that can bounce dust into raindrops. And tiny fluctuations in temperature shape snowflakes and frost. And it all goes to show how our weather is endlessly fascinating. A stunning display of magic and spectacle performed in front of us every single day. Even when conditions are wet and miserable, there are amazing events going on just behind the scenes. And though it may seem that only extreme weather is worthy of our attention, the weather around us every day is equally full of wonder. This is not freak weather. It's our weather, and it's astonishing.